everybody, and welcome to Mathematical Induction with me. Today we're going to be using fancy transitivity from our rules of inference. Remember, P implies Q, Q implies R, then we get that P implies R. Before we even get mathy though, I want to start with a problem that appeals to intuition. Let's say we've got some dominoes lined up, and each domino is going to be set so it knocks over the next domino in line. If I knock over the first domino, what can I conclude about any other domino? Well, it's going to get knocked over. How do we know that though? Like, yes, we've seen it happen, but what is going on logically that lets us make that conclusion? Let's try and dissect this sentence right here. So we've got n dominoes lined up so that each knocks over the next. That is equivalent to saying for like the kth domino in line, we will get the next domino where P of x equals domino x is knocked over. So if domino x gets knocked over, then this sentence right here says the next one in line gets knocked over. Then what else did I say? I said if I knock over the first domino, so I said that P of 1 was true. So domino 1 is knocked over. So then what came next? I said, what can I conclude about any other domino? So I said it will be knocked over. Basically what I'm trying to prove is for any number n, of course we're going to be dealing with natural numbers because there's no such thing as -1 dominoes. So for all of natural numbers, I want to be able to assume that P of n was true. So no matter how many dominoes I get lined up, if I knock over the first one, I get to assume that any other domino gets knocked over. Okay, so I have translated, hopefully successfully, dominoes falling over into math symbols. Just to reiterate, in general, what induction is going to look like is we want to prove that for all n in the natural numbers, we're going to get some statement P of n is true. And the big idea behind the proof is, well, P implies 2, 2 implies 3, and that goes all the way down to P of n. So as long as we get P1 is true, we get to conclude any other number. So that's basically summarized right here. Boils down to proving two things. We need the implication step to hold in general. So that would be like, I need P of, I think I used K on the previous page to imply the next one is true. And we need the first PK case to be true. In this case, I had 1 was our first case. But it might be the case that 0 is the first case. You can tell pretty easily by looking at the problem. I'll have examples for you guys. All right. I feel like a broken record at this point, but I am going to say it again. When you are doing your induction proof, what you will always have is you will start with your base case. You will prove P of 1 is true, maybe P of 0, depends. And then you will have your inductive step where you're going to say, I assume that Pn is true, and I need to prove that Pn plus 1 follows, because if that works, then I get this whole domino effect. Okay, let's try and take this for a run. So example 1, I have this summation just in case you don't remember what this summation means, it means these terms right here. I'm claiming that the sum of these terms is going to be equal to 2 to the n plus 1 minus 1. How do we prove that? By induction. There's no way to like move everything to one side or something and then like get something that you can solve or something. Induction is really good for when you have proofs that involve like formulas involving the natural numbers. If you have the real numbers, you immediately know you're not dealing with induction. Okay, so proof. I'm going to specify that I am doing it by induction so that everybody knows what was going on in my brain. First thing we have to prove, it works at the very beginning. So that's what we always call the base case. And then you have to check, what's my base case going to be? So right here, you can see that n goes down as low as 0. So this is an example where n is 0 is your base case. So we've got base case, n equals 0. That would mean you only have the very first term. So 1 would be equal to 2 to the 1 plus 1. Nope. 0. N is 0. Minus 1 like that. And then that indeed checks out. 1 will be equal to 2 minus 1. That's fine. I like check marks saying, just to indicate, yes, I thought about this. Induction step. So this is when we're going to be trying to prove that if it works for the nth one, it works for the n plus 1 one. You can use k's if k's make you feel better if you don't want to like double use notation, but it is very common to just always use n. So I'm going to go ahead and use n. Why? Because everybody else is doing it. So we assume the nth case is true. We're going to assume this. And what we want to get is prove this formula holds for the n plus 1 case. So you want to go everywhere you can find an n and replace it with n plus 1. So we want to show this summation going up one extra term is going to be equal to this. But that is not my proof. So let's put that to the side. I think it's useful to have this just as a goal. It's nice to know where you're headed. So now what we're going to do is we're going to start with, we know we have this formula, we want to get here. That is our goal, and we are going to use our assumption somewhere in our argument in order to get there. So let's start with the summation. And then it's easier, I think, to visualize in this written out form. So let's go ahead and do that. Write out the first couple terms, write out the last n terms. So these would be the last n terms. So this is where the assumption is going to come in. We made an assumption about the first n terms. See, the assumption goes up to the first n. So that's this piece right here. So let's take that. I'm going to rewrite it as the sum so that we can see these pieces moving. So this guy was not part of the up to n sum. There we go. And our assumption has to do with, we know what this is equal to. So now we can substitute that in. It's equal to this. So substitute that in, 2n plus 1 minus 1 plus this extra term. And now from here, our goal is to simplify it to look like this. Oh, I missed my plus 1 over there. Okay. So you can see right here, we have 2n plus 1, 2n plus 1, we have 2 of them. So let me give myself a little bit of room. There we go. So we have 2 of them, so we could write it like this, or simplify that a little bit further, and now we have 1 more 2 in our exponent, like that. That is the formula we were trying to get to. So now we have connected this n plus 1 part of our formula to this n to the n plus 1 formula using our assumption, and we are now done. Let's take that for another run. Let's try it with this derivative problem. So what we're going to do, we're going to start with our base case. The base case is going to be n equals 1. We don't want to talk about zeroth derivatives here. So we're dealing with the first derivative. That means that we've got f of x is equal to 1 over 1 minus x. We're going to take the first derivative and make sure that it fits inside this formula. So then df dx is going to be equal to, remember that it looks like this, and we're going to use the power rule, and that's where that negative comes from. And then by chain rule, we get another negative. 2 negatives make a positive. And that indeed fits into this formula, because 1 factorial is 1. And then if n was 1, which we said n was 1, we could write our exponent like this. Okay. The formula holds for n equals 1. Now, time for our inductive step. Here we get to assume that the nth derivative of f is going to be equal to that formula, and we want to show it the n plus 1 case. So then, just like I did before, I'm going to give us a goal. We're going for the n plus 1 derivative being equal to this factorial over 1 minus x n plus 1 plus 1, because I replaced this n right here with n plus 1. Okay, so here's our goal. Move him up here out of the way and begin our proof. So we're going to start here with the left-hand side. So okay, and what do we know? Well, we know that we could write this n plus 1 derivative with using this term right here so that it looks a little bit more familiar. So like we can take one extra derivative of the nth derivative, so we can split it up like this. Here we go. And now that we have this sitting here, I can say, oh, I know what that equals. I can plug that in. Why? Because that was our assumption. I should be careful. Write the word assume. There we go. So we are assuming this piece right here. Okay. So if we plug that in, that means we are now taking the derivative of this term right here. We know how to take a single derivative. We're going to use the power rule. And we're going to get a negative n plus 1 to come down. N factorial 1 minus x n plus 1 plus 1. So looking pretty good. And then by chain rule, we get that negative 1 coming out from inside here. And then we can do the same. 2 negatives make a positive. To simplify this a little bit, And then I'll move that n plus 1 to the numerator as well. Okay. And then this piece right here, that's just n plus 1 factorial. And so we have gotten to the formula we were trying to get to because we wrote out our goal, and so we know where to stop now. Done. Okay. So those are two basic examples for induction. Let's do a generalized induction. Really, all that means is we're starting somewhere that isn't n equals 1 or n equals 0. All the same steps that we're going to try and do. We're going to do our base case. We're going to do our assumption, where we assume it holds for n, and then we're going to move on and try and prove it for n plus 1. So all that stuff is going to stay the same. However, this formula is only going to work for n bigger than 4. If you try plugging in n equals 1, you end up with 1 is bigger than 3, and you're like, no. But as soon as n is bigger than or equal to 4, this formula will work. So our starting place is now not going to be n equals 1. So here we go. Here's our proof. We're going to say we're doing it by induction. And here's our base case, which is going to be the smallest n that we can use, which is n equals 4. So we go ahead and we plug 4 in, so 4 factorial, which is going to be equal to, give me a moment. No, I'm going to write it down. Let's see, so that's going to be 24. That's what it is. And then if we plug it in on this side, that would be 3 times 4, which is 12. We know 24 is bigger than 12. There we go. So that's our base case, and we are done. Now we just have to do our inductive step. So we are going to assume it holds for n. And then just like before, I'm going to write out what I want to show, which is n plus 1 factorial is going to be bigger than 3 times n plus 1. I'm going to put that off to the side somewhere so that I can keep track of it. But that is not my proof. So let's start with the left-hand side. I've got n plus 1 factorial. I know how to break that up so that I can see the n factorial explicitly, and that seems like a good idea since our assumption involves n factorial. So I'm going to write it as n plus 1 times n factorial. Now that I have the n factorial, I'm going to say, hey, I have an assumption about that. Let's plug it in. So n plus 1, oops, that's not an equal sign, is going to be bigger than 3n because we're replacing this n factorial with the 3n, and we know that the 3n is going to be smaller. So then I look at this and I'm like, that's not entirely the same. Let's try and maybe rearrange this a little bit. This n right here is kind of a problem. It would be the same if we didn't have that n. I'm like, well, do we need that n? Like, I know that n is bigger than 4. So what I could say is that this piece right here, so this piece is bigger than this because n is bigger than 1. But then if we just replace it with 1, that is indeed exactly what we were looking for. And we are done. Okay. So that's all I've got for induction. It boils down to I have to do my base case, which is going to be the smallest case that matters, whether that's n equals 0 or 1, or maybe they're going to be more specific and say something more like 4 or bigger. base case is the smallest n. We plug it in. Those are usually like pretty easy to get through. And then the inductive step is where the like the harder piece of the argument comes in. We have to make an assumption about n, and then we go through and we try and prove it for the n plus 1 case. So I like, again, to write down the formula so that I have a nice end goal to get to. And then once we have proven this using the assumption that we made, we are then done with our induction proof. Okay, and that's all I've got for you guys for right now. So I'll see you all later. Bye.